Let's imagine we've got a random variable that's binomially distributed. It counts the number of successes in n trials where the probability of success at each trial is p, and the probability that we get r successes is n choose r, p to the r, 1 minus p to the n minus r. So for example, when n is 4 and p is a third, we can calculate the probability of 0 successes, of 1 success, of 2 successes, of 3 successes, and of 4 successes. Now I'm going to do something rather surprising. I'm going to write down a polynomial. We all know what a polynomial is. It's a bunch of powers of x with numbers in front of them. 7x to the power of 5, minus 5x to the power of 4, plus 3x to the power of 3, and so on and so on. Or we could use t instead of x, and the numbers I'm going to use in front of those powers of t are those probabilities that we've just calculated. So I'm going to start with the probability of 0 successes, and times that by t to the 0. Then the probability of 1 success times by t to the 1. The probability of 2 successes times t squared. Probability of 3 successes times t cubed, plus the probability of 4 successes times t to the 4. And we're going to call that polynomial g, or g of t. Now here's my polynomial again. But remember that those numbers all came from probability calculations. So here it is again, with the probability calculations and the powers of t all simplified. And of course that looks just like a binomial expansion. It looks like the binomial expansion of 2/3 plus t over 3 to the power of 4. And if you're not sure about that, just use your binomial theorem on that bottom line and you'll quickly get back to the previous line. Now, we've got two forms for gt. We've got this one here, the expanded form, and this one here, the factorized form. And we're going to use both of those to figure out what the expectation of x is. And we're going to do it by differentiating. Here it is again. And that's easy to differentiate. Here it is. And you'll see in a minute why I've bothered with 0 times that probability at the beginning. Now I'm going to put t is equal to 1. And you can see what we get. We get 0 times the probability that x is 0, plus 1 times the probability that x is 1, plus 2 times the probability x is 2, and so on. In other words, what we get is the expectation of x. So now we know that g dashed of 1 is the expectation of x, but remember we've also got a different form of gt. It's the factorized form. And we can also differentiate that. Bring the power down, reduce the power by 1, and of course times by the differential of the bracket. Now when we put 1 in for t, what do we get? Well, 2/3 plus 1/3 is just 1, and 1 cubed is 1. So we've got 4 times a third, or n times p. So there it is, expectation is 4 times a third. And what we're going to do now is exactly the same process, but instead of using 4 and 1/3, we're going to use n and p. So we'll start off by defining our polynomial in exactly the same way, except of course there's rather more terms, so I guess we won't write them all out. And we can simplify that with our sigma notation. And that has a special name, the probability generating function. If you're not sure about the sigma notation, just put in all those different values for r from 0 to n and you'll see easily that you get back to what you want. And we can put in the formula for probabilities that we know for the binomial distribution. And now we see we can simplify that a little bit by putting the p's and the t's together. Now before we go any further, we're just going to remind ourselves what the binomial theorem says. A plus b to the n is a to the n plus all this other stuff that we know and love by now. We can put that in our sigma notation. And again, if you're not sure about that, just put in the values for r from 0 to n, one after another, and you'll get back to the previous line. But of course, that looks rather like this formula for the probability generating function gt. What's our value of b? Well, it's pt. And what's our value of a? Well, it's 1 minus p. So instead of a plus b to the n, we can write 1 minus p for a plus pt for b to the power of n. Now we've got our two different versions of g of t, and I'm going to differentiate them both. So here's the first one. This is the expanded version, and it's easy to differentiate. And then we can put t is equal to 1. And we recognise that immediately as the formula for the expectation of x. Now let's look at the factorised version. And we can differentiate that. Don't forget to times by the differential of the bracket, which is p. Then we can put t is equal to 1. And we get np. So clearly, expectation of x must be np. Now let's see if we can do variance the same way. And this time we're going to start with g dashed of t and differentiate twice. But again, we're going to use both our versions of gt. So here's the first one, the differential of the expanded version, and we'll differentiate it again. Again, easy to do. And now we can expand that first bracket. Oh no, let's put in t is equal to 1 first. And now let's expand that first bracket. And now let's split it up into two sums. And clearly the second one of those sums is just the expectation of x. But that first sum, that one there, that's clearly going to have something to do with variance because we know that appears in the variance formula. Here is our variance formula. And we can make that sum the subject of that formula. So we can rewrite what we got for g double dashed of 1, but using variance of x plus expectation of x squared instead of the sum of the r squares times the probabilities. All right. Now let's look at our other version of g of t, or g dashed of t, the factorised version, and we're going to differentiate that. Bring down the power. Again, don't forget to multiply by the differential of the bracket. Now we'll put t is equal to 1, because that big bracket to the power of n minus 2 just becomes 1. Okay, and we can put that equal to that thing we got a minute ago. Now we know that expectation of x is np, so the expectation of x squared is n squared p squared. Now we can make variance of x the subject. Now we can expand the brackets. Now we can simplify and factorise. And we've got our formula for the variance of x. So let's just summarise. If x is binomially distributed, expectation of x is np, and the variance is np 1 minus p.